You are listening to The Vocal Technologist. Spoken tech for your ears.
If you work in engineering, especially anywhere near AI and big data systems, you know the feeling.
Oh, yeah.
The pace of change is it's relentless. It feels like you're trying to build something stable, but the ground is constantly shifting under your feet.
It really is. And just keeping up with what's a real shift versus, just another buzzword, that's a full-time job in itself.
Totally.
We've really hit a point where the old tricks don't work. You can't just throw more computers or more storage at the problem anymore.
The easy wins are gone.
Gone. Success now is all about, I'd say, three things: pure efficiency, really rigorous governance, and getting every last drop of performance out of that super expensive hardware like GPUs. It's a precision game now.
Okay, so let's unpack this. Let's dive into some of the critical advancements that are really defining modern data architecture right now.
Sounds good.
We want to cut through some of that complexity for you and really highlight the strategic shifts that are completely changing the data workflow.
Where do we start?
I think we have to begin with a concept that's been a bit of a holy grail for years. Treating your data exactly like you treat your software code.
Right.
Because historically, the biggest roadblock was just managing these huge data sets for testing without spending days, making slow, expensive copies of everything.
And it's so fascinating because the data world is finally adopting the best ideas from source control, specifically from Git.
So things like LakeFS or Nessie or Tigris.
Exactly. Those tools are absolute game changers because they give you instant branching, zero-copy cloning, solid rollback capabilities.
And all on petabyte scale data.
All on petabytes. And you can do atomic snapshots. So if I'm running some big transformation and it messes up the production environment.
You don't have to wait for the overnight backup restore.
No, you just you snap back to the state it was in 5 minutes ago. Instantly.
And that's all done with metadata, right? You're not actually copying the raw bytes.
Precisely. It's all managed in the metadata layer, which is why it's so fast. And that just accelerates your whole CI/CD cycle. But that data as code idea has to go deeper. We need to talk about SQL.
Right. We have to get past SQL being this ad hoc script you just, run in a UI somewhere.
Exactly. That copy, paste, and tweak approach is a nightmare for scalability. A truly robust system needs spec-driven jobs stored in Git, with templates, with validation.
Dry runs, cost limits.
Critically, cost limits, all deployed through CI. It turns a random action into a predictable, observable asset. No more silent failures or, runaway cloud bills.
And when you're running all these jobs in a big distributed system, reliability is everything, especially with retries. Which brings up idempotency keys.
Oh, they're essential. Absolutely essential for what we call exact once processing.
Because most message systems only guarantee at least once delivery.
Right. So you need a way for the consumer, the thing receiving the message, to safely ignore duplicates. And a dependency key, which is often just a simple UEDI, gets attached to that message.
And the consumer just logs that key and says, nope, seen this one before.
Exactly. It can be safely ignored.
I saw some notes about engineers using the database's transaction log, the WAL, for this. Why is that a win?
It's an efficiency play. The write-ahead log, or WAL, is already the definitive ordered record of all committed changes. So by using the WAL position as your key, you're leveraging an existing guaranteed sequence. It's often way more efficient than managing a separate, massive table of UIDs yourself.
That makes a lot of sense. So that gives us a really solid foundation for reliable engineering.
It does.
But, a robust system is only half the fight. It needs to be running on useful data. We've kind of gone from data scarcity to, data gluttony.
That's the perfect term for it. I've seen it called data obesity, and it's a real problem. The numbers are just staggering.
What are we talking about?
Companies today are storing 2.5 times more data than they did just 5 years ago.
Huh.
But only a tiny fraction of it ever gets analyzed.
And the immediate thought is, oh, the storage costs must be insane.
But that's the trap. Storage is cheap. It's only about 8% of the total cost of ownership. The real cost is the operational complexity, the cognitive load on your engineers.
And the compliance risk.
The compliance risk is huge. Over 2/3 of all stored data, that's 68%, is what we call dark data.
So it's just sitting there, unclassified, uncatalogued.
Untouchable. And it's not just sitting there costing you pennies for storage. It's actively hurting you. It degrades your analytics, it can poison your LLMs with bad information, and it's a massive regulatory time bomb.
So how do we get out of this mess? How do we shift from just hoarding data to actually using it strategically?
Well, there's a really interesting proposal for a new metric, the Data Sustainability Index.
Okay.
Instead of just measuring how many terabytes you have, this index calculates how much useful compute or business value a dataset actually generates relative to its total cost and complexity.
It forces you to justify the data's existence based on utility.
Exactly. And the thing that makes that even possible is metadata.
Rich, contextual metadata.
The unsung hero. Always. Lineage, glossaries, tags. That's what turns raw data into a real asset. It's what gives AI models the context they need to not just, make stuff up.
But this is where big projects so often fail, right? A company decides to build the one true enterprise knowledge graph or ontology to rule them all.
And it almost always fails.
Why is that?
Because the premise is flawed. You're chasing a static perfection that's impossible. Getting consensus and stability across a huge dynamic organization. It's just unobtainable. Good solutions have to embrace the mess. They need adaptive models and continuous reconciliation.
So stop trying to freeze an ocean. Let's talk about a concrete example of using data smarter. The Etsy case study on A/B testing was fascinating.
It's a brilliant example. They managed to cut the duration of their A/B tests by up to 50%.
50%? How?
Using a statistical technique called predicted control variance, or PCV.
Yeah.
It's actually really elegant.
So what's the mechanism? Before the experiment even starts, they use features they already know about, a user like their purchase history or visit frequency, to predict what the result would have been without any change.
Okay.
Then they just subtract that prediction from the result they actually see. It's like filtering out all the expected noise up front so you can see the real signal from your experiment much, much faster.
You reach statistical significance in half the time. That's a huge product velocity gain.
Huge.
Okay, here's where it gets really interesting for me. We're moving from cleaning up data to pure performance engineering, squeezing every last bit of speed out of that expensive AI hardware. The term that keeps coming up is continuous batching.
Continuous batching is a massive breakthrough for LLM inference, a total game changer.
So with traditional batching, you send a bunch of requests to the GPU, and you have to wait for the slowest one to finish.
Exactly, which means your GPU is sitting idle a lot of the time. Continuous batching fixes this by mixing requests at the individual token level.
So as soon as one sequence in the batch is done, it's out.
It's out, and a new one immediately takes its place in the batch. The GPU's cores are always busy. The result is just dramatically higher throughput, lower latency, and it makes the whole economic model of serving these giant LLMs actually work.
We saw some pretty wild numbers from Meta on this kind of thing. They built a platform called Zoomer.
Yeah, Zoomer is designed to hunt for these inefficiencies that humans just can't see at that scale. And the results, for their ads models, they cut training times by 75%.
So 75%.
Which also meant 78% less power used. And maybe the craziest part, they boosted their inference QPS by almost 20% by fixing a single inefficient memory copy that the platform found automatically.
That's incredible. It just shows that these tiny little architectural bottlenecks can have these massive global consequences.
It proves that optimization can't be a manual, ad hoc thing anymore. It has to be an automated platform-level function.
Okay, let's switch gears slightly to another AI performance challenge. Search at a massive scale. Let's use Uber as the example. How are they keeping search results so relevant while running this thing globally and efficiently?
They are masters of the trade-off. They keep their recall rate above 95% with a big two-tower neural network, but the real magic is in the embeddings and the quantization.
Okay, let's break down some of the acronyms because there are a lot here. They're using something called MRL.
Right, Matryoshka Representation Learning. Think of it exactly like a Russian nesting doll.
I was hoping you'd say that.
It means their high-quality embedding, say 512 dimensions, can be chopped down to a much smaller size, like 128 dimensions, without losing much quality. This lets them switch between high-precision or low-latency modes on the fly.
Which saves compute time and storage, and they combine that with scalar quantization.
Yeah, they move to in7 quantization, which is just using less precision to store the numbers. That, plus some other clever tricks, got them to 50% latency reduction and 50% storage savings. It's just layer upon layer of smart optimizations.
A perfect example of that strategic efficiency we were talking about. So let's go back again to the foundations, the databases and engines that power all of this. What's changing at that base layer?
Well, one of the most surprising trends is the rise of serverless scalar.
Really? Quite.
Yeah. Platforms like Turso and Cloudflare D1 are wrapping it to provide this super high-performance storage right at the edge. You get incredibly fast reads and scale to zero economics.
For so long, the goal was just more complexity, more distribution. Why is simple suddenly winning again?
Because for a ton of modern apps, especially read-heavy ones, managing a giant distributed SQL cluster is just total overkill. This model centralizes the writes, but pushes read replicas out to the edge. It kills complexity and cost.
A strategic retreat from complexity. I like that. What about the big traditional players? I saw PostgreSQL 19 got a big speed boost.
A huge one. And it was a change in the query optimizer's logic. Before, Postgres would often join huge tables together first and then do the aggregation.
Which creates a massive intermediate table.
A massive one. The new optimizer is smart enough to aggregate the data before the join. For common GRU UPBI queries, people are seeing up to a 5x speedup with zero code change.
That's just free performance.
Pure velocity. And we're also still seeing these highly specialized engines pop up, like data fusion for graph processing.
In Rust, right.
Right. It implements this big star, small star algorithm, and for in-memory graph stuff, it was 4 to 5 times faster than Spark graph frames, using half the memory.
So you trade distributed scale for raw single node speed.
It's another one of those smart trade-offs.
Let's wrap up with a couple of real-world stories that just highlight the discipline required to operate at this level. Stripe's migration platform is legendary.
It is. They built this zero downtime platform that can migrate petabytes of data with traffic cutovers measured in milliseconds. That's just an insane level of operational excellence.
And on the flip side, we saw the fragility when a tiny ClickHouse permission change at Cloudflare
Cascaded into a global CDN failure.
It's such a powerful lesson, isn't it?
It really is. It proves that error handling, whether your system crashes hard or just degrades gracefully, that's not a local code decision. It has to be a global architectural choice you design in from day one.
And one last positive story. Zalando and data sharing.
A great one. They switched to Delta sharing to give thousands of their partner brands secure, real-time, zero-copy access to data. For Zalando, it saved them the equivalent of about 1.5 FTEs worth of manual work per partner.
That's efficiency institutionalized. You know, what this all points to is this powerful convergence. You've got strategic data cleanup on one side with things like Git workflows and governance.
And then hyper-efficient infrastructure on the other, like continuous batching or even just simpler serverless tech.
And that combination is just unlocking these incredible performance gains and cost savings.
It proves, I think, that the value of data is finally being judged by its utility and its agility, not just its raw volume. If you're still just collecting for the sake of collecting, you are paying a very steep tax in cognitive load, risk, and wasted compute.
So, what does this all mean? If the cost of storing that dark data isn't really the problem, but the cognitive and compliance cost is, how should you redefine what success looks like in your own organization? Is your focus still on collecting the most data, or are you focused on maximizing your data sustainability index?
That's the question.
That's something for you to think about until next time.
Spoken Tech for your ears.